Amplitude. An electronic control circuit driving a linear motor produces the oscillatory amplitude in much the same way as in a permanent magnet speaker. When the square wave driver has a positive polarity, it drives the electrical coil and the attached piston forward in the direction of the patient. This results in an inspiratory phase. When the polarity is negative, the electrical coil and the attached piston are driven in the opposite direction, resulting in an active expiratory phase. To activate the oscillator, press the Start-Stop button. The green LED will illuminate, showing the oscillator circuit is energized. The mean airway pressure must be at least 5 centimeters of water pressure in order for the oscillator to activate. The oscillator may be stopped without complete loss of mean airway pressure. This allows for auscultation of the patient without the loss of lung volume. Piston displacement is controlled by the power control, which is a graduated 10-turn potentiometer. The small lever on the control is a lock. It is set by moving the lever down. To unlock the control, lift the lever before turning. The displayed amplitude is the peak-to-peak oscillatory pressure measured at the airway opening. It's important to note when observing the pressures that the pressure amplitude reported by the instrument is the sum of both the inspiratory and expiratory phases of the ventilator. It will be significantly attenuated at the alveolar level by the resistance of the endotracheal tube. The same mechanism can result in severe detriment to ventilation. As secretions accumulate in the endotracheal tube, airway caliber is reduced, resulting in a lower tidal volume. Clinical strategies for HFOV call for the initial setting for amplitude to be based on chest wall movement. This movement should be visible from the chest to the upper thigh. Subsequent changes to the amplitude are made based on the patient's PCO2. In the event that the amplitude has been maximized, consideration should be given to decreasing the frequency. Maximal amplitude can be recognized when an increase in amplitude of 15 to 20 centimeters of water pressure yields no improvement in the PCO2. A frequency setting that is too high may result in an elevated PCO2 that seems refractory to significant changes in the amplitude setting. It's also important to rule out other possible causes for an elevated PCO2 before deciding on a final course of action. For example, a dislodged endotracheal tube or the need for airway suctioning could easily be the cause for little or no response to manipulation of amplitude. In this case, chest wall movement will either be diminished or completely absent. The piston position and displacement indicator provides the operator with information on the position of the piston relative to its mechanical limits and the control settings. The 3100B features auto-centering and thus requires no intervention by the operator to maintain piston centering. Inspiratory time percent. The inspiratory time percent sets the relative duration of the successive positive and negative polarity voltages from the square wave driver. Since this parameter is set as a percent of cycle time, absolute inspiratory time is a function of oscillatory frequency and inspiratory time percent. For most applications, this parameter remains at 33%. In applications where the patient presents with refractory hypercapnia, in the face of maximum ventilatory support, increasing the inspiratory time percent may improve ventilation and may improve lung recruitment. The effect of increasing inspiratory time percent is most pronounced at lower frequencies, such as those found in larger patients. Use caution when increasing inspiratory time percent in patients needing longer exhalation time, as air trapping may result. Frequency. The breath rate of the 3100 is expressed in Hertz. 1 Hertz is equal to 60 cycles per minute. Typical applications utilize frequencies of 4 to 6 Hertz, or 180 to 360 breaths per minute. Unlike conventional ventilation, in which minute ventilation is expressed as frequency multiplied by tidal volume, minute ventilation for HFOV is expressed as frequency times tidal volume squared. It's important to understand this relationship, since it demonstrates that even small changes in tidal volume may elicit a significant change in minute ventilation. As discussed in the previous section, altering the voltage to the linear motor by manipulating the power control directly affects the amplitude. Since a given power setting represents a specific electromagnetic force acting on the piston, the duration of the force is controlled first by the frequency and second by the inspiratory time percent. As frequency decreases, total cycle time increases, thereby increasing the duration of the time the force acts on the piston. This results in an increase in tidal volume. This means that the frequency behaves counterintuitively to conventional ventilation, and that decreasing the frequency will increase minute ventilation. Once an appropriate frequency is arrived at for a given patient, it usually does not change for the duration of therapy. Alarms. Thumbwheel controls are used to adjust the set maximum and set minimum mean airway pressure alarms from 0 to 59 centimeters of water pressure. The set maximum mean airway pressure will provide an audible and visual signal when the alarm threshold has been reached. Additionally, activation of this alarm will trigger the auto limit system. This system will briefly open the limit valve on the inspiratory limb of the circuit. The circuit pressure will fall by approximately 12 centimeters of water pressure. At this time, the valve will repressurize to its operational state. However, the visual alarm will remain on. In the event that the high mean airway pressure alarm condition persists, the limit valve will continue to cycle until the fault condition is resolved. Pressing the Reset Power Fail button will reset the visual alarm. If the alarm for the set minimum mean airway pressure is triggered, audible and visual alarms are activated. The audible and visual alarms automatically reset upon resolution of the fault condition. Activation of the backup mean airway pressure alarms will also trigger audible and visual alarms. These backup alarms are factory preset for greater than 60 centimeters of water pressure for the high alarm and less than 5 centimeters of water pressure for the low alarm. When these alarms are triggered, the oscillator will stop and the circuit pressures will be vented to ambient pressure. Bias flow will continue. Bias flow is maintained, allowing the patient the ability to breathe spontaneously at normal atmospheric pressure. Once an alarm condition has been resolved, the circuit must be repressurized manually by pressing and holding the Reset Power Fail button. The Alarm Silence push button silences all audible alarms for 45 seconds. Once activated, this button illuminates a yellow LED. The alarm silence will remain active for the full 45 seconds. The Power Fail alarm provides an audible and visual signal, indicating loss of electrical power to the ventilator. This alarm is also triggered when the ventilator is powered off. To silence it, press the Reset Power Fail button. These three yellow LEDs are caution indicators, with no accompanying audible alarm. This LED indicates a low source gas condition of less than 30 psi for either of the high-pressure gas inlets. The battery low LED means that the power failure alarm battery, located in the rear panel of the ventilator, must be changed. The oscillator overheated LED signals that the internal oscillator coil temperature has reached approximately 150 degrees Celsius. The oscillator stopped indicator means that the oscillator system is enabled, but the amplitude is less than or equal to 7 centimeters of water pressure. An audible tone will accompany this red indicator and will automatically reset once the alarm condition no longer exists.